Hello everyone, welcome to my next video. It is not a tutorial video, it is a video which is related to the research paper. So before I start of this video, I want to introduce myself. I am Sahil Verma, working as application engineer on the well-known company Impulse Technology. Research papers which is published by the IIT Madras, and we are going to that graphs. We are not move on that theory parts, but we are just showing the graphs how you can calculate that type of properties. So before we start of this video, you can see my previous video. In here we have discussed about the set for softwares, like new modules have added thermal modules, and in the previous emission, depth diffusion, absorption and advanced optics modules we have already discussed in a previous video. We are directly going to open research papers is published by IIT Madras. You can see that paper simulation strategy for organic LED with spectral dissimilarity between photoluminescence and electroluminescence spectra. So it is a main topics that related to that research papers, and abstract you can study about these things, and it is an introduction. We are not going to inside of this theory parts because we have not that all collected data, but we are going to show that how you can simulate that graphs, like normalized intensity and wavelength, current density and versus voltage graphs, luminance and voltage graphs, external quantum efficiency limitation versus voltage graph, current efficiency versus current density graphs, EQE versus current density, and EL spectra and wavelength. So you can see that graphs on the set for softwares. It is generally comparison between the experimental data versus simulation data. In this set for software, photoluminescence spectrum files you can directly import and you can simulate that property. In experimental data, you can take and compare with this simulation data. You can see that its energy levels that attached in the research papers you can also see on the set for software. It is a simulation setup that we have taken. Like at the starting point, you can see that abstract a red phosphorescent bottom emitting organic light emitting diodes compressing with host co-host dopant system fabricated using vacuum thermal evaporations methods. Also introduction parts, and it is a experimental setup. You can see what type of OLED device stack we have taken. So you can see that, and material and process chambers, OLED fabrications, device characterizations. We are not directly going on that input parameters because we have not that input parameters. It is a confidential. So but we are going to show that graphs how you can find and how you can compare with random data. Like in here you can see OLED stack details, glass, indium tin oxide and HATCN and hole transport layers, EML, electron transport layers, LIQ and aluminum. That OLED stacks you can take on that set for softwares. As respect to that 165 nm, 10 nm, 100 nm and 160 nm, 30 nm, ETL, 40 nm. So this type of thickness you can also provide. In the bottom side you can see indium tin oxide act as a anode and aluminum act as a cathode. So you can also consider that anode and cathodes as well. As in here you can see HATCN used as a hole injection layers and LIQ used for the electron injection layer, and EML consists of the host, co-host and dopant mixtures proportion 65%, 35% and 5% respectively. So this type of OLED stack you can directly create on the set for softwares. So first I am going to create OLED stacks related to this details. Now I am going to open set for softwares. Click on the right side, run as an administrator. It is a set for softwares and GUI. We have already discussed about their GUI, and I want to give the short description about this geographical user interface of the set for software. If you want to create your new simulations files, click on this. If you want to open your logistics example, move with this. For the save your files, you can use that both options. For example view, you can click on this tab. If you want to see that stack editor, you can click. In the set for 6 versions, new material database have added, like number of the refractive index files you can see, and passive optics modules. These are the 5 modules: absorption modules, emission modules, scattering modules, drift fusion modules, thermal modules. It is a master equation mode. It is a sweep mode where you can sweep your all parameters. It is a optimization modes, and it is a fit emission zone modes. In here you can create your layer stacks. In here you can provide your input parameters, and in here you can check your stack preview. If you add new layer, you can add from here these tabs, and for the interface you can click on these tabs. Upside, bottom side, and whole structures changement, you can use this type of tabs. For the modules, layer structures, you can also see on this tabs, and it is a script modes, and it is a console view active when that layer stack have created and you have run these files, and it is a result view. Now I'm going to create that OLED stack created in the research paper. So one by one I'm going to give in here that name. First you can provide in here that glass as per the research paper, ITO. In the set first you can provide unlimited layer stacks, hole injections layer, STL, EML, ETL. You can add more layer in here. Give electron injections layer like you, and aluminum. As per the layer stacks and thickness value, you can also provide in here. Thickness you can see nm, micrometer, mm, and quarter wavelengths. You can give in here that one. ITO you can consider 165. Hole injections layer consider 10 nm. STL 100 nm. In the research paper you can see in your track 100 as well as 160 nm. So first you can simulate with the 100 nm thickness, and then you can simulate with different project name 160 nm, and then you can compare. EML 30 nm, ETL 40, LIQ 3, aluminum 150 nm. Now one by one you need to import the refractive index files, because which layer each wavelength dependent, so you need to import their refractive index file as well as. So you can activate that absorptions module, and you can see in here the refractive index files. First you need to import ito.nk. Import directly ito.nk file. You can see different refractive index file that are given, and that data which are not provided you can collect from that material database. Number of the files have added in the set for 6. You can see. You can import any of the ito.nk files. ito.nk. Same you can apply for the HATCM. You can import that refractive index files. HTLs, one of the whole transport layer you can import. In the research papers maybe that's layer names for the HTL are not provided. We are considering one of the HTL layers in here, and pb.nk. For the EML we are going to import in here the CBP. If you have that EML layers which have that like EML consists of the host, co-host, and open mixtures, so you can also import this type of layer as well as, but we are considering one of the email layer in here. And electron transport layer we are going to consider BCP, and LIQ you can import like this, and same you can import for the aluminum. Generally we are majorly focused on that graph parameters, how you can simulate that type of graph provided on that research paper like this. You have imported that refractive index files one by one. You can see on the absorption settings, SIP and single wavelength are given. You can consider SIP parameters for the wavelength according to your choice and according to your research papers as per given. As you have considered one step, you can take more steps, reduce your calculations files. Illumination spectrum file, you can see sun spectrum files are given. Wavelength, incidence angles, default parameter we are considering in here. You can see that stack preview we have created in here. As per that given OLED stacks details, we have considered one of that random stacks file with respect to that given thickness. So you can create same like this set for softwares. Now we are going to provide in here that electrical parameter as per the research paper. You can see this type of energy levels. So now I'm going to take that electrical parameter as well as in here that given ITO act as the anode and aluminum act as the cathode. So we will consider in the same in here activate drift fusion modules and ITO as take as the electrode. Work functions as selected with that same energy level. So we are going to consider in here same 5.5 and aluminum you can consider electrode 3.2. In between that electrode you need to consider semiconducting layer. So one by one you can take that semiconducting layer. So you can choose like this. You can see that energy level are not matched with that research paper. You need to import one by one semiconducting layer files. So move with this semiconducting tabs and import HATCN files. You can see different material files are given. You can see they have not that input parameters. We are going to import that HATCN electrical material files in here. Like you can see HTL hole injection layers for the HTL HATCN. You can import these files. You can see that HOMO and LUMO value and all the parameters have automatically fill in here. Excitant, traps, mobile ions and recombinations. Same for the HTL. You can import one of the HTL files npb.em. Email file you can import like co-host and host type of materials at that distance. So it's not totally matched, but we are going to import that gtcta motor 7.em file. We are going to just import. If you want to edit some parameters, I will also edit that parameters, but first we need to import that files. That's the reflective index files you have imported, so you can import that same bcp.em file. You can import in here that liq files, etl files. One of the etl files you can import, it is a electron injections layer, so you can import. But you can see that energy level are not matched with this energy levels. You can see two types of energy levels are given. Energy diagram for the OLED stack with conventional type implementation and alternate way. So you can choose in here the HOMO and LUMO value as per that research papers. So you can match this type of energy level. Like we have going to choose one by one. HATCN 5.5, but LUMO level you can see 1.253. HTL you can consider in here 5.5 and 1.253. EML layer you can choose 5.75 and in here you can choose LUMO 2.6. ETL you can choose 6.37 and LUMO you can choose in here the 2.69. 5.7048 HOMO and LUMO you can choose 2.886. So now you can see that energy levels it is a match with these research papers. It is just showing that how you can put that value in this given tabs. It is editable tabs. File import generally mean to provide that respective data automatics in here if you have not provided, because setforce have that library. So you can see that electrical material files and reflective index files have provided in here. If you want to edit some parameters you can edit. You can see that density of types are Gaussians that have selected. Excitant you can see annihilation rate, excitant proton quenching for electron, excitant proton quenching for the holes. Like in the research papers you can see flowing rates fit the experimental object roll off like TTA, TPQE, and for the holes you can see inhalation rates, triplet inhalations. So this type of data you can also provide on this setforce softwares in here. Inhalations rates, like if you enable this tab TT singlet generations, excitant proton quenching for the holes and electrons, you can provide that data. Like if you want to change that radioactive decay rates you can change, non-radioactive decay rates if you want to give in here that value you can give. And resistance rates, like you can provide in here that's value. And proton quenching for the holes you can provide that value for the holes. And in that tabs you can see energy transfer rates. If you add, you can also give in here the energy transfer rates, TDF for the low energy to high energy. So most tabs are provided in here, but if you click on that master equations tabs, like if you enable this, and you can see that conching singlet front conching rates for mobile straps, triplets, alterations rates. So for the singles, triplet, so that data you can also provide in here for the singlet and for the triplet. You can give in here that data for the anions, cations respectively. For the advanced calculations, you can move as well as in here. We are taking for the respect selective layers, and here you can like input parameters have completed in here, but you have provided different value. If you move on that SIP tabs, you can move, you can see the optical data, different type of data are given. You can SIP your parameter with respect to this data if you have provided voltage, glass, thickness, you can see. So you can SIP most of the parameters in here. If paper based on the OLED, we need to consider in here the one of the emissive layers. We need to activate emission modules and email taken as a emitter. And in here that photoluminescence spectrum files you can import, and you can see different tabs are given in here. You need to import one of the photoluminescence spectrum files, like you can see alpha and PD, and you can import that files. Unit probability and powers for your graphs, you can see. Distribution emission need to be coupled with the drift diffusion and absorption. You can use the recombinations coupled. Dipole orientations, you can see isotropic, parallel, perpendicular. In that research paper we have considered isotropic. Emission intensity, conversion efficiency, you can take accordingly. If you move on that SIP, you need to define in here that SIP parameters as well as you can see that emission angles. You can give in here the ranges 0 to 90, you can consider. You can take in here that step 10. Before of this, you can see the electrical source voltage. You can consider in here that voltage 4.5. So different tabs are given. You can move with this emission setting. You can see different modes are given: spectrals, SIP wavelength, emission angles, quenching. You can choose force reset or that resets. You can choose quenching as well as. You can give in here that your simulations file name, OLED research, and click on the run button. You can see that type of graphs. Same reduces that steps, and then again you can see that graphs. We are majorly focused on this current efficiency, luminance, peak emission intensity. It graphs related to the emission angles, absorption, layer absorptions, reflectance, current efficiency, luminance, peak emission intensity. Generally, you can see that graph related to the emission angles. We again move with this shift setting tabs because we need to that find in here that voltage and current density related graph. Again move with these tabs and add one more layer modes and select in here that voltage. Give in here that 0 to 8 0.09, and it will take too much time if both shift will be occur at the same time. So you can disable with emission setting and only shift with voltage and click on the run button. You can also take email as a transparency, and now you can see that the result portions, you can see VOC, ZSC and fill factors. So that type of results you can see. Electrical integrated, current balance, device current. It totally depend on that input parameters: electrical power, internal quantum efficiency, power conversion efficiency, band diagram, charge generation, charge density, electrical field, mobilities, potential and recombinations. It is a emissive properties, linear efficiency versus voltage graph you can see in here. Current efficiency versus voltage graphs. You can also zoom like these parameters. x-axis, y-axis you can change according to that parameters, and like if you click on that log, that graphs will change, and abs and inverse you can change according to that x-axis, y-axis, like log, abs, inverse. So you can see that's view, but it is a current efficiency versus voltage graph. Luminance, peak emission intensity you can see versus voltage graphs. Radiance, stat contribution, it is absorptions profile. Device efficiency versus voltage graph, EQ versus voltage graphs. You can also change that logs, apps, inverse. So it is just a viewpoints. Generated photons, reflected, transmitted. Spectral parameters like absorptions, layer absorptions, you can see one by one from here. Spectral emissions graph, normalized emission and white emissions, like it is a emissions. You can also edit that x-axis plot versus voltage with respect to that whole voltage, all car. If you want to change in here that emission intensity, so you can edit like parameters. Now you can see on that result tabs this type of voltage and luminance, current density versus voltage graph you can see in here, as well as like maybe the results are not whole matched because input parameter are not considered as per that research papers, but you can calculate like this type of value or properties in here. Same if you move with this current types of graphs, you can move with this source voltage current. You can select in that simple volt currents. It generally used for the device operated voltage. Change in here that currents you can see in the same ranges, but if you want to change you can change and give in here that another names and click on the run buttons. Same type of results you can see, read to the current balance versus currents, currents, device voltage, electrical power, internal quantum efficiency, log, apps, inverse you can change. Same you can choose for that electrical profiles, emissive profiles, numerics, but in here you can see that current versus current efficiency, and if you change it that's log, apps, inverse, normal. So you can see same for the luminance, peak emission intensity, photocurrent, radiance. If you change, so you can see that according to the SIP parameters you can also collect that data, image or different things. Device efficiency, generated photons, normalized emission and white emissions. If you sip on that different parameters, like if you move with these emissions you can see position, lifetime, quantum efficiency, dipole orientations, luminance spectrum data column. So you can sip and then you can got different results and you can match from this research papers, and then you can compare with that experimental data. Maybe that's once again I want to clarify these things. Maybe the results are not completely matched, but I'm just showing how you can find that luminance versus voltage type of graphs. And you can also publish your papers like IIT Madras using the Setfor software. So you can also use this type of softwares to find your respective properties and compare with that experimental data. Some value that given in that research paper. So I'm just considering and try to find that results. So now I'm going to end here my this video. If anyone have that query related to this, please ask in the comment box, as well as my email are given. So you can also contact with my emails and email us. And who has not seen it my previous video, please check out the playlist. Thanks for watching this video.